Hello. Hopefully this is working out all right. All right. Well, we'll just hang out. When somebody shows up, we'll start answering questions and see how that goes. If you get in and you have questions for calculus, just let me know. All right. Well, hello, everybody. See a few people are viewing. If anybody has questions for the calculus review, let me know. If you'd like to get started, I could talk about things. You just got to kind of, let me know what you want to talk about first. All right. Just because I don't know what else to do, I'm going to start talking, and I'll start off with the beginning. And so, if you are in the class, you want to follow along, I'm just going to run through the practice final that I had posted and that we ran through. So, as I said, if you guys have questions, type in. I'll jump around. I'll skip ahead to where you're at. I'm just going to pull up the final so I have something here. And so the first one we started off with was limits. So what are limits? Well, let's start off graphically, and let's suppose I have a picture. I'm going to draw something up here. Let's say it looks like this. And let's see, we have this. And I'll pick a different color because that looks hard to see. All right, so if we want to talk about limits, we're going to talk about what happens to the y values as the x value gets close to something. So that is, as x gets close to some value, what does y do? And so if we look at 2 here, we want to know, okay, as x's are getting close to 2, what's happening to the y values? And so if we look at our graph up here, what we're going to do is we're going to follow in. And so we're going to find first the limit from the right. So we start from the right, follow the function in, we come over, we get closer to 2, and then what's happening to the y values is the whole time here I've tried to draw it so that it stays close to 1, and so the y values are going to be approaching 1 from the right. On the other hand, if we approach 1 from the left, that is, we approach 2 from the left, so when as x goes to 2 from the left, we're going to do the same thing, but we're going to come in from the other side. So we're going to start to the left of 2. We're going to move over until we get to 2. Once we're at 2, we'll notice that, okay, the y values are still at 1. So the limit from the left and the limit from the right as x goes to 2 is 1. So that means that the two-sided limit, the limit as x goes to 2, is also equal to 1. So remember, that's the important thing here is we're coming in from the left, we come in from the right. If we get the same value, then the limit exists and is equal to the value that we got. Now, if we look at 1, the limit as x goes to 1 from the left and the right, we'll notice that as we go to 1 from the right, we have that the y values are getting closer and closer to 1 because we have a constant function here and they're equal to 1 all the time. Whereas if we come in from the left, my y values get closer and closer and closer to 1 as well. Therefore, what we have is that the limit from the left is the limit from the right is equal to 1. Therefore, the two-sided limit as x goes to 1 is equal to 1. However, we note that f of 1 is actually equal to 2. So the limit is not equal to the function value. So as far as the limit's concerned, it doesn't matter what's happening exactly at the point 1. It just matters what happens when we're close. So as we get close to 1, we have that our y value is getting close to 1, so that's our limit. Now, later on in this problem, it asks about continuity. And so for continuity, the function value does matter. In particular, we're going to have that a function's continuous if the limit exists and is equal to the function value. So what we have here at 1 is that the limit exists and the function exists, but the limit is not equal to the function value. Therefore, this function would be discontinuous at 1, and so that's going to show up towards the bottom of the problem for number 1. If we look further, another place that we might find of interest is that if we look at 0, so the limit as x goes to 0 from the right of f of x is, we're going to follow our function in now from the right. We're going to move in to the left until we get close to x equals 0. And so now when x is close to 0, my y values are getting close to 2. So the limit from the right as x goes to 0 is equal to 2. On the other hand, the limit from the left, well, the y values are getting closer and closer to 1. So what we get is that my limit from the right as x goes to 0 is going to be 1. Therefore, the two-sided limit does not exist because each one-sided limit is not equal to each other. So when we have this happen, we have the limit does not exist. So if the limit doesn't exist, again, this is a discontinuous function at 0. So if I want to find all the points of discontinuity within the domain -1 to 3, the points of discontinuity here would be 0 and 1. Now, I didn't draw a point in here that did this, so I'm going to redefine this function a little bit. And let's say that my function had looked like this. Trying to make that darker so it's easier to see. But as we look at 2 again, the limit as x goes to 2 is again 1, because the limit from the left is the limit from the right. And in this case, the function value is also 1, so therefore it is continuous at the point 2. However, what we get here is that if we wanted to find points of or points where this is non-differentiable, we notice that the derivative does not exist if our function is discontinuous. So we'd have that this is non-differentiable at the point x equals 0 because it's discontinuous due to a jump discontinuity. The derivative does not exist at the point 1 due to a hole discontinuity, but also the limit does not, or the derivative does not exist at 2. Now, this is because we have a sharp corner, and remember that if we drew the secant lines from the right, they would look like this. And if we draw the secant lines to the tangent line from the left, it would look like this. And so remember that the derivative is a two-sided limit. So that is what we've seen here is that the slope of this line from the right is not the slope from the left. Therefore, the slopes of the secant lines, or the limits of the slopes of the secant lines, are not equal to each other. Therefore, we do not have that the limit exists, and we do not have a derivative at the point 2. All right. So one more thing here is that if we now talk about what was the derivative, to recap, then the derivative was the limit, or the derivative at a point is the limit as h goes to 0 of f of a plus h minus f of a all over h, where this is the slope of the secant line through the point close to a, and then we take the limit as h goes to 0. We just said here it has to be a two-sided limit, so it has to be the same from both sides. Now, what we have on the other hand is that, let's suppose that I ask you what is the limit as h goes to 0 of f of, let's say, 1.5 plus h minus f of 1.5 all over h. Well, what we're going to get here is that we've written out, this is just the derivative, so f of a plus h minus f of a all over h. So that's the derivative at the point a equals 1.5. So now if we want to find the derivative at the point a equals 1.5, we're going to do the same thing we did over here where we draw in our secant lines until we get the limit. And so if we draw in our secant lines here at 1.5, we pick 2 points, we connect those dots with the line. So coming in from the right, we get that line, coming in, or from the left, coming in from the right, we get this line. So what we get is that as my second point approaches 1.5, the line we're going to get is just a horizontal line through y equals 1. So what we get is, because it has a horizontal line, the slope then would be 0. So therefore, this limit does exist and is in fact equal to 0, or is the slope of the line. Now, if we wanted to do that somewhere else, let's say we wanted to find f of 2.5 minus f of 2.5 all over h. What we'd have to do here is the same thing. Sorry, I keep bending it down because the eraser falls, because I don't have a nice little tray here to hold it up. But, all right, going back to this one, at 2.5, if we try to draw on the secant lines again, what we're going to end up with is, we'll pick this point as 2.5. I'm going to pick a point less than it and draw the secant line, pick a point less than it and draw the secant line. So if I draw the tangent line from that side, I get that. And then on the other side, I'm going to pick a point to the right of it, draw the secant line, pick a point to the right, draw the secant line, so that my tangent line looks like that. And notice that this tangent from the left is the same as the tangent from the right. Therefore, we have that the two-sided limit will exist, and the slopes of the secant lines go to the same spot. So the tangent slope does exist. Now, at that point, we would say, well, what is that slope is going to be this limit. So how would we find that slope is, well, now we just need to approximate from the graph. So if we start here, we're at the point what looks like 2.5 was my x. But if I draw, my y value looks like 1.5. On the other hand, I'm going to pick another point, let's say at 2 here. And then at 2, I'm going to draw up and draw over, and that looks approximately like 2, 1. So what I have now is I have 2 points on the line. And once I have 2 points on the line, I can find the slope of the line just as the change in y over the change in x. So what I'm going to get here is just, well, the change in y is 1.5 minus 1 over 2.5 minus 2. And so I get 0.5 divided by 0.5 is 1. And so this limit, the limit as h goes to 0 of f of 2.5 plus h minus f of 2.5 all over h is indeed equal to 1. All right. So now that's the majority of what the first problem is going to look like. Is we'll have an arbitrary function drawn up on the graph. This is what we saw in the practice exam. You'll have to, from that graph, determine what limits are going to be and determine what does the y value do as the x value approaches some number from the left, from the right, or the two-sided limit. Or then you'll have to figure out, well, what's this limit going to be? Well, notice if you see something like this, it is just using the limit definition of derivative. So what they're really asking you to do is find the tangent line and then find the slope of the tangent line by using 2 points on the line to find the slope. It's nice if it's horizontal because then you just have a slope of 0 and you don't have to go through do this much work. But it is possible that the line will not have slope 0, so you'll have to find 2 points on the graph and calculate the change in y or the change in x. Now, when you do that, just as a note, you don't have to be precise. I rounded here. You'll notice that I said this looks like 1, but on my graph it looks like 1.1 or something. As long as you're close, that'll be fine. You can't expect perfection from a graph because, well, it's hard to tell exactly where the points are. So as long as you pick the points close and you get a close value, that'll be enough. What I wouldn't want to happen, or what I would mark off points for here, is that if you got a slope of -1 here, let's say, clearly that slope is not negative because it is an increasing function. Therefore, we would have to have some type of positive number. If somehow you got out 2, that'd be fine. If you said 100, that'd probably be a little too high. So just keep in mind that you want to try to get an approximation, but it doesn't have to be exact. All right. So I'm just moving on to the next one on the practice exam. Since nobody's having any questions as far as I can tell, if by chance you have questions, you are welcome to email me. I have my phone here. Well, for my students, you're welcome to do that. You have my email already. Just as long as I get the questions, I'll try to do whatever you ask. So let me know. But continuing on, number 2 on the practice exam looks pretty similar. Again, it's just a function and they want us to find some limits. The distinction here is that they could be infinite limits. So if we see something like this, I'm going to have, let's say, something like that, and then something like this. So if that's f of x, then if I ask something like, what's the limit as x goes to 1 from the left of f of x? We're going to do a similar thing to what we had before. The distinction being is that we're going to have a different answer. So if we let x get close to 1, we're going to start off here and we're going to follow the function. And we follow the function as x gets closer and closer to 1. But what we notice is that our function keeps getting bigger and bigger and bigger. And so the x values never reach 1 if we keep following that line. They just get closer and closer. So what we end up with is that, well, this means that our function is growing without bound. It is getting arbitrarily large in a positive direction. So because of that, we would say that the limit from the left of f of x as x goes to 1 is equal to infinity. So now that limit actually does not exist because it's not a number. Infinity is not a number, but we notice that it does not exist in such a way that it is getting arbitrarily large. So we can say that the limit from the left is infinity. If we look at the limit as x goes to 0 from the right, x goes to 1 from the right, what we're going to do is exactly the same process, except for start on the right, follow it in. We'll notice a very similar thing happening. The only distinction being is that my values are getting arbitrarily large in a negative direction. Therefore, what we would say is that the limit from the right is negative infinity. Hence, what we have is, remember, since the limit is infinity or negative infinity, we have a vertical asymptote here. Since the left limit is not equal to the right limit, we have that the two-sided limit does not exist. We can't say any more than that. If we had both of them being infinity, it still technically does not exist, but we could say the two-sided limit does not exist in such a way it gets arbitrarily large, so it is infinity. But we can't say that in this case because they are going different directions. The other one that will come up is all right. So supposedly there's a few questions, post it on the video chat, which I don't see. Oh, thanks, Julie. Now I'm getting emails in. This is the first time at this. That's why I'm having troubles with the chat thing here. Let me see if I can find that just real quick. Sorry, guys. This is the first time at this. That's why I'm having troubles with the chat thing here. Let me. All right. All right. Well, I'm getting some emails, so I think that might be easiest since I have no idea what I'm doing. Maybe I'll try to figure out how to get the chat going eventually. First one I see is, could you answer 7 log of x over 3 plus log of x from the math review? All right, let me look at that, make sure that I understand that one correctly. All right, so, sorry, the first one was from the final review. We have 7 natural log of x divided by 3 plus log of x, and I want to find the limit as x goes towards infinity. All right, as I do this one, I'm going to play around with the computer to see if I can find your guys' chat. But if I'm taking the limit, the first thing I should do is what? Well, the first thing I should do is plug in the number or see what happens as x goes towards infinity. And so if I do that, what I end up with is, well, 7 times natural log of infinity, which is 7 times infinity is infinity. And on the other hand, we have 3 plus natural log of infinity. And natural log of infinity is infinity. So 3 plus infinity is, well, that is also infinity. So what we end up with is infinity over infinity. All right. So infinity over infinity. And if I have infinity over infinity, that means that I can do what? Well, that means that I can use L'Hopital's rule. So in order to use L'Hopital's rule, that says to take the derivative of the top over the derivative of the bottom. And so let's go ahead and do that. And what I get here is the derivative of 7 natural log of x is equal to, well, I'm going to pull out the 7, and then I'm going to get 7 times 1 over x. And so I get the limit as x goes towards infinity of 7 times 1 over x. And then if I take the derivative of the bottom, well, the derivative of 3 is 0, and the derivative of natural log of x is 1 over x. So what I do here is, well, I look at it again, and I want to determine what my limit's going to be. So therefore, as I look at my limit, I am going to get, well, 7 divided by infinity, divided by 1 over infinity. If I track that through, I actually get 0 over 0. So I would have to actually use L'Hopital's rule again. However, if I track that through, I actually get, if I, instead of just going through and using L'Hopital's rule again, what we want to do first is we always want to simplify if possible. And so in order to simplify, what we're going to do is we'll notice that we have the 1 over x over 1 over x. So what we get is these cancel out. and all I'm left with is just a 7 here. So I get the limit as x goes towards infinity of 7, which is equal to 7. So that would be the answer from that one. Just looking at the other ones that they had listed there. The next one was the limit as x goes towards infinity of x cubed over e to the 3x. And so if I want to find the limit as x goes towards infinity of x cubed over e to the 3x, I am going to do the same thing I just did, in that I am going to plug in infinity and figure out what happens there. Now, when I'm doing that, what I get is on top 3, or infinity cubed is infinity over e to the 3 times infinity is e to the infinity. Well, e to the infinity is infinity, so we get infinity over infinity. Now, since we get infinity over infinity, what we can get is, well, we can use L'Hopital's rule. So what L'Hopital's rule says is that we can take the derivative of the top over the derivative of the bottom, and what that gives us is the limit as x goes towards infinity of 3x squared over the derivative of e to the 3x is, it's a chain rule, so the outside's e to the I, the inside's 3x. So the derivative is going to be the derivative of the outside's e to the I is e to the 3x times the derivative of the inside is 3. So we get 3e to the 3x. And so what I end up with is 3e to the 3x here. And so if I look at this, what I get again is, well, I can simplify, so the 3's are going to cancel. So that'll help me out as I go along. And what I get is infinity over infinity. All right. So that was exhausting. But did we get somewhere? Yes, in fact, we did. And so what we get is, sorry, I'm still trying to figure out where some of this stuff is. Oh, there's the chat, and I don't know why I couldn't see it before, but I can see it now. Hello. All right. I'm going to have this up on, I do have the chat up now, but it's going to be on my phone, so I'm going to have to look back and forth between the computer just to let you know. Going back to this one, though, I did want to finish this up. I have infinity over infinity, so really what I do is I do have to use L'Hopital's rule again. And so I get the derivative of the top is 2x. The derivative of the bottom is, again, for the same reason, 3e to the 3x. And what I get is infinity over infinity. So if I can simplify, I will. And if I can't simplify, well, then I can't. So I just continue on with this. And so then what I end up with is, all right, so L'Hopital's rule again is the derivative of the top is 2 over 3e to the 3x. And now I get 2 over infinity. And so 2 over a really big number is a really small number. So I get out 0. All right. Now, see some of your chats here. I'm going to go back to, I'm just going to start at the beginning from what you guys put in the chat now. So I'll start answering those questions. And so the first one I see was from Fatima, was question 12, part B from the practice exam. So question 12, part B. Let me pull that up. All right. So for that one, what we have is, I kind of have to do both parts. There's the linear approximation, and then we have to use the linear approximation to find what some value is going to be. In order to just give you something a little bit different to view, I'm going to do a different function, but it should be the same process. So the idea is that we have something like, what is sine of x near x equals pi? So find the linear approximation to sine of x near x equals pi. And so as I was telling you guys in class, what we end up with is that the linear approximation really just means find the tangent line. So the best linear approximation is the tangent line, so we find the tangent line. If we want to find the tangent line, we have to find the line. So we get m times x minus x naught plus y naught. And then what we get from here is, well, I need to find the slope, I need to find x naught, and I need to find y naught. And so what's going to happen is x naught's given to me, that's just the pi. And then y naught for the tangent line is just going to be the function value at the point that we're given. So we would find f of pi, which is sine of pi, and sine of pi is 0. All right, to find the slope then, we find the derivative at the point. So we first need to find the derivative. So we get the derivative of sine is equal to cosine of x. So the slope is going to be cosine of pi, which is -1. So what we get is that the linear approximation is negative x minus pi plus 0. And so the best linear approximation to sine of x near pi is y equals negative x minus pi plus 0. Now, with that said, we're pointing out that if I were to draw this, then this line would be close to it. And so the second part of the question says, well, use this to find or approximate sine of 3. I know they're using the fifth root in the problem, and I'm using sine here, but the idea is that you had a function up here, and they're going to plug a number into the function. So what they're really saying here is that if I want to find sine of 3, I'm trying to approximate f of 3. So that is, sine of 3 is equal to my function with 3 plugged in, but that's approximately equal to my line, because my line is an approximation for my function with 3 plugged in. So what I do here is I say negative, and now instead of x, I get 3 minus pi. So I would get pi minus 3, or as an approximation, about 0.14. And so I would say sine of 3 is approximately 0.14. And so that's what they're looking for there, is to take that, to turn it into a line, and then use the line that you just found and plug in the number that they've given you into the line to find an approximation. Notice now that finding sine of 3 by hand would be extremely difficult, but just approximating pi and plugging 3 into a linear function is something we can do by hand, and that's the whole purpose of the problem. And so that's what they want there. All right, good. I'm glad that's making sense. All right, some more. Next one was more limits as x goes towards infinity. We talked about a couple of those. Let's talk about, I guess, one more. Which problem were those? Like 4B in the sample exam. So we'll look at some of those. All right. So before you get to 4B, I'm going to look at 4A again. And so I'm going to take the limit as x goes towards infinity, because that's what we asked is, let's suppose we had 2x squared minus 3x plus 1 all over x squared plus x minus 2. And so if I want the limit as x goes towards infinity of that function, what I'm going to do is I can plug infinity in again, and then I'm going to get infinity minus infinity plus 1 over infinity plus infinity minus 2. And what's infinity minus infinity? Well, that's one of those indeterminate forms. If I follow this through, though, I get a lot of stuff going on, and it's basically just going to become an infinity over infinity. And so what we can do is we can use L'Hopital's rule here, and then we'll use L'Hopital's rule. We would get 4x minus 3 over 2x plus 1, and then we would get infinity over infinity again, and we could use L'Hopital's rule again. Now remember that we had that shortcut here, though, was instead of trying to go through, and we could have done this on the x cubed and the e to the 3x one as well, but instead of trying to go through, what we could do is say, well, in this case, the only thing that matters are the dominating functions. And so if we take the dominating functions, what we end up with is, well, we can ignore the 3x because 2x squared dominates it. We can ignore the 1 because the 2x squared dominates it. And the bottom, we can ignore these portions because x squared dominates those. And then what we get is, well, instead of having to go through the work of using L'Hopital's rule, we're remembering the ordering of domination, we get just 2x squared over x squared is 2. So the limit as x goes towards infinity of 2 is just, well, it's constant, so that's 2. So now the reason why I wanted to do this one first before doing the next one is because the next one, if we tried to use L'Hopital's rule directly, we're just going to end up making lots and lots of work for ourselves. So I'm just going to look at what are the dominating functions on top and bottom. And so if I do that, what I end up seeing is that, well, the 9x squared dominates the 1, so I can ignore that. The x dominates the 10, so I get the limit as x goes towards infinity of the square root of 9x squared over x. Now I could use L'Hopital's rule, but because it is still infinity over infinity, but instead I'm going to simplify. So I get the limit as x goes towards infinity of, well, the square root of 9 is 3, square root of x squared is x, all over x. And now x over x will cancel as well. So we're just left with 3. Therefore, what we get is all right. Sorry, I'm just trying to ask a question here. Okay, for the problem you just went over, when else can we not use L'Hopital's rule? I do want to point out you could have used L'Hopital's rule here. It's just that it's going to take a lot longer. So it would still work out. You could do some simplification. But the point is that anytime you're taking the limit as x goes towards infinity, we want to try to simplify before we use L'Hopital's rule just to make it less work on ourselves so that we can get through a little bit quicker. So if we're going towards infinity, we want to ignore everything but the dominating functions on top and bottom. That's how we simplify. That's how we make things easier on ourselves. Again, you can do it without it, just like we could have done it without it up here. But then what we end up with is that it just takes longer. So if we simplify first, we can get the answer out much quicker. Now, as far as limits, while we're on the idea is when can you do one that you can't use L'Hopital's rule, is remember that I told you the only time when you won't be able to use L'Hopital's rule is for the limit definition of derivative. So let's go ahead and look at one of those. Do you guys want to do a square root one or do you want to do a fraction one? First one to respond, I'll do that for the limit definition of derivative. All right, we'll do the square root. Thank you. So what's going to happen is, like the one we had on the practice exam, they had a fraction, so we went through that one in class. We could also have something like, what's the square root of x plus 4 to find the derivative. And so if we use the power rule, we can get the answer out fairly quickly. We get x plus 4 to the 1/2. Take the derivative as, well, the derivative of that is going to be 1/2 times x plus 4 to the negative 1/2 times the derivative of the inside is 1. That's a chain rule, right? Derivative of the outside is 1/2, inside to the negative 1/2 times the derivative of the inside. And so we get 1 over 2 square roots of x plus 4. And again, they're going to give you that solution when you're using the limit definition. So what we have to do is we have to do this one the long way. And so what we're going to do to start off with is the limit definition of derivative was the limit as h goes to 0 of f of x plus h minus f of x all over h. Now, in this case, what we get is we have to find each of these. So I just start off and I'm going to say, what is f of x plus h? Well, f of x plus h is the square root of x plus h plus 4. Because instead of x, I'm just plugging in x plus h. So I get my x plus h plus 4. Now, the next thing is, well, if I can simplify that, I'm going to. And if this had been a polynomial like x squared, you could distribute the x plus h plus 4 squared out. You can simplify that and combine like terms and things like that. But for both the square root one and the fraction one, we can't simplify yet. So we have to move on to the next part. And we're going to get the square root of x plus h plus 4 is f of x plus h. And then we're going to subtract off f of x. Sorry, x plus. So f of x is the square root of x plus 4. So I take this minus this. Now, it doesn't look like we can really do much here to simplify it because we can't directly combine terms. But since we're going to need to, remember that the trick for square roots was multiplying by the conjugate. So what we're going to do is multiply by the exact same thing we have up here. But instead of the minus in between them, I'm going to put a plus. So I'm going to leave everything alone inside of here, everything alone inside of here. I just have this whole square root, this whole square root. But instead of subtracting, I'm going to add. And that is my conjugate. But since I'm multiplying by that, I also have to divide by that. So that I have the same problem. And so again, that's the trick for square roots. So if we had a polynomial, we'd simplify and factor things out. If we have fractions, we combine them using a common denominator. And for square roots, we multiply by conjugate. And it's one of those 3 types of fractions that will show up on the test. Most likely either one just like this or one just like on the practice exam where you have a fraction. Now, if we multiply these out, the reason why we did this is that the square root squared cancels. And so I end up with, on top, x plus h plus 4. And then this square root and squared cancel, but I have a negative times a positive. So I get minus x plus 4. And now the idea here is that this one times this one cancels out with this one times this one because of the same thing, just one's positive, one's negative. And so all I'm left with is this over the bottom is still square root of x plus h plus 4 plus the square root of x plus 4. All right. Now that we've done that, we can do some more simplification. And so I'm going to distribute the negative sign. So I get a negative x, a negative 4. And then I have x minus x cancels. 4 minus 4 cancels. And so all we're left with on top is an h. And on bottom, we have the whole square root of x plus h plus 4 plus square root of x plus 4. Now, just because my chalkboard's much smaller than it would be in the classroom, I'm going to pull this up into my limit right away and say this is the limit as h goes to 0 of h over the square root of x plus h plus 4 plus the square root of x plus 4. And then to divide by h, I'm going to multiply by 1 over h. So the third step would be to divide by h. I would normally do that off to the side. But as I said, I'm kind of running out of room, so I'm just going to do that up here. So what I end up with is, well, the h's cancel. So I just get a 1 here and a 1 here. And so I get the limit as h goes to 0 of 1 over the square root of x plus h plus 4 plus the square root of x plus 4. At this point, I have a limit to calculate. And so now we're going back to our last problems. The first thing we should do is plug in the number. So if I plug in h equals 0, I get 1 over the square root of x plus 4 plus the square root of x plus 4. And so there are no more h's in there. There are x's, but that's okay because the h is the one that's changing, not the x. So this is a number, our limit's calculated. So you can write this as the square root of x plus 4 plus the square root of x plus 4 if you'd like. But to get the form that we originally had, we just add those. There's two of them. So I get 1 over 2 square roots of x plus 4. And so that would be my derivative, which is exactly what we got using our chain rule and power rule combined. So that's a good thing that looks like we got the right answer. Is that clear enough for you guys? Do you want to do another limit definition, or is that enough? I'll give you a second here to let me know. All right, one more with fractions. Sounds good. So if we do the limit definition with fractions, it's going to be very similar, except for, again, the trick's going to be find a common denominator. So we just go through that. Let's suppose that my function is 1 over, let's say 2x. So now again, we can use the power rule and say this is 1/2 x to the negative 1/2. This is negative 1/2 x to the negative 2. So what we want to do then is figure out, can we show that using the limit definition? So here is our derivative, so we can keep that in mind as we go. And so we're going to start off the same way we did last time, was just find f of x plus h. So f of x plus h is equal to 1 over 2 x plus h. And so what I get is 1 over 2x plus 2h. So I was trying to simplify there. Technically, you could leave it like this if you want. Just because I'm so used to simplifying, I want to distribute that out. So I get 1 over 2x plus 2h. And so now what I would do is I've simplified that as much as I can. I can't do any more because I can't distribute the bottom. So the next thing I'm going to do is take f of x plus h minus f of x. And I'm going to end up with 1 over 2x plus 2h minus 1 over 2x. Now, what we need is we need a common denominator. So in order to find a common denominator, I'm just going to multiply this fraction by this denominator and this fraction by this denominator. So what I'm going to end up with is 2x over 2x times 1 over 2x plus 2h minus 1 over 2x times 2x plus 2h all over 2x plus 2h. I know I ran out of room there, so this is a 2x plus 2h, 2x plus 2h. And so if I combine those together, what I get is the bottom here is going to just be 2x times 2x plus 2h. And so what I get up top is, well, the first portion is 2x, and then minus this portion over here is 2x plus 2h. Sorry, I needed a parenthesis here, not here, because it's going to be 2x times 2x plus 2h. I put it in the wrong spot. I apologize for that. So what I get here then is, well, now I can simplify the top. If I distribute the negative sign, I get negative 2x and negative 2h. but then I have a positive 2x and a negative 2x cancel out, so I'm left with a negative 2h up top. And so then what I can do is, well, just to make my life easier, I'm going to cancel out the 2's. And so what I'm left with is, up top I have negative h over x times 2x plus 2h. And then remember the next part was to divide by h. So instead of dividing, I'm going to multiply by 1 over h. And again, normally I would do this as an extra step, but because I'm running on a board, I'm just going to put it up here. And so what I get is now the h over the h cancels, which is what we were hoping for, because with an h and an h, we had a 0 over 0. We wanted to cancel that out. And so now we're left with a negative 1 over x times 2x plus 2h. Now that we've done that, we can now calculate our fraction, our limit. So if I calculate my limit, I get negative 1 over x times 2x plus 0 is negative 1 over 2x times x is 2x squared. Remember, again, the x is not h. H is the thing that's changing, so x is considered a number in this case. So we end up with is just negative 1 over 2x squared, which is exactly what we started with, which is good, because otherwise I would have made a mistake at one of the points. So we do get out that that is our derivative, and that's what we're looking for there as far as our work goes. All right. Is that clear enough for everybody on the limit definition of derivative? I know this is a hard one because we don't get to use L'Hopital's rule or making you go back, and there are different tricks for each one. It's not just a general, here's the process, do it. We basically have 3 different cases you have to memorize, was the fractions, the square roots, and then if you have something like x squared or x squared plus 2, you then have the factoring part. And so it's tough just having different techniques for each one that comes up instead of having one rule that works all the time, which is the great thing about L'Hopital's rule. But again, this is the one problem exam where you are not allowed to use it. All right, you're welcome, Jermaine. Some antiderivatives. Yep, I will. I'm just kind of scrolling down, making sure I got to all the earlier ones. There's one more, and then I'll do antiderivatives, was the square root of 3 plus cosine of 3x. And then we'll look at the antiderivatives after we find the derivative of this function. All right. So I had the square root of 3 plus cosine of 3x, and I want to find the derivative of that. So now, in order to find the derivative of that, what I have is, well, the first thing I want to notice is that it is going to be a chain rule because I have an inside function. And so my inside function is I'm just going to let it be the whole inside, 3 plus cosine of 3x. Now my outside function is going to be the square root. So I'm just going to say outside is the square root of I. Now, in order to do the chain rule, we need the derivative of the outside times the derivative of the inside. So we're going to take the derivative of the outside. Well, in order to take the derivative of the outside, anytime we have a square root or a cube root or an any root, I'm going to rewrite that using a fractional exponent. So I get I to the 1/2. So now the derivative of I to the 1/2 is 1/2 I to the negative 1/2, because we multiply by our exponent, subtract 1, so we get 1/2 I to the negative 1/2. Then I need to find the derivative of the inside. Well, the derivative of 3 is just 0, so what I really need to do now is find the derivative of cosine of 3x. So actually, what I would do here is I would go off to the side and say the derivative of cosine of 3x is more complicated than just your average derivative. I can't just guess the answer. Some of you may be able to, and if you can, that's great. But if not, what we need to notice is that this is a chain rule, and my inside function here is 3x. My outside function is cosine of I. So what I get then is that the derivative of cosine of I is negative sine of I, and the derivative of 3x is 3. So if I multiply those together, I get negative sine of I times 3, and then I have to plug I back in to finish this off, so I get negative sine of 3x times 3. Now, remember, this was just a side problem for my other problem, so now that I have my answer, I'm going to bring that back here, and I'm going to say, okay, well, the derivative of this is, and I'm going to pull the 3 out front just to make it look a little prettier, but I'm going to get negative 3 sine of 3x. So what I get now is the derivative of the outside times the derivative of the inside is the derivative of this thing. So the derivative of the outside is 1/2 times the inside is the negative 1/2 times the derivative of the inside we just said was negative 3 sine of 3x. And then the last thing we need to do here is we have this I in here still. So we're going to plug in what I was, and we're going to get 1/2 times 3 plus cosine of 3x to the negative 1/2 times negative 3 sine of 3x. And so that one is a chain rule within a chain rule, but then we're able to get our answer out. All right. I hope that one helps. So let's see, some antiderivatives. So I'm going to go to, you're asking for number 17. So I'm just pulling that up real quick. All right. Now I'm just going to address this one first, and then I'll go back, or B first, and I'll go back to A, is what is the antiderivative of the square root of x cubed plus 1 dx? All right. Now, I tried to say this in class, and so I just wanted to be clear here. When they want us to find this one here, they really just wrote a really bad question. This will not be on the final because the techniques that we have don't lead to an easy answer for this. What you can do is you can do something very creative and substitute a couple different times, and you can still end up using substitution, but it's a really not a nice function. And to point that out, what I'm going to do is I'm just going to say, let's let I be x cubed plus 1, because if I look at this, I can't guess the answer, so I'm going to think that it's going to be a substitution. What I'm going to get then is di is 3x squared dx, because di is the derivative times dx. So dx is di over 3x squared. And so what I would do is I would substitute in, and I'd get the integral of the square root of I times di over 3x squared. And what you'll notice here is that the i's don't cancel, and the x's don't cancel, I'm sorry. So you have both i's and x's in there. So we have two variables when we have to integrate. And so what's going to happen is, well, we can't integrate because we don't know how to integrate a function of two variables. Yes, that is something that will show up in Calc 3, but no, that is not something that will show up in Calc 1 or 2. So no, there is no way that we know how to do this. So I'm going to say that this one hasn't shown up on a final ever, and yet they keep putting it on the practice final. I'm just not really sure why they do that. So I'm just going to leave it at that and say the substitution didn't work. Technically, we should go back and try a different substitution. Could I try x squared or x cubed instead of x cubed plus 1? No, that's not going to work either. I think the substitution was like x to the 3 halves. If I do that correctly, I can end up canceling things out, but that is a really awkward function. So I'm just going to say ignore this one and do the other ones, and you will be fine if you can get through the other ones. I hope that's okay. All right. So now, if I do the other ones, what I have is start off with sine of 2x plus e to the negative x. So I'm going to find the integral of sine of 2x. And so I'm just going to do this one in pieces, because if you're given one that has multiple parts to it, you just want to do it one at a time and then add them all together at the end. So I'm just going to focus on the integral of sine of 2x for now. Now, again, we talked about this with the chain rule, is that if you're okay with kind of guessing what the answer is going to be, that's fine. But if you're not, take this one step at a time. So what I'm going to do here is say, okay, well, I can't guess what the answer is going to be. So I'm going to say we have to use substitution. So using the substitution, I'm going to pick my inside function is 2x. Once I have my inside, I say that di is the derivative. So the derivative of 2x is 2 times dx. And then I solve for dx is just di over 2. So following along the same process, I pick the inside function. Di is 2 dx. Dx is di over 2. So if I plug in, I get sine of I times di over 2. And now notice, as is supposed to happen, the x's are gone. We're just left with i's, so that now we can integrate because it's just an integral with i's. The other thing is this is a 2 on the bottom. That's a divide by 2 is the same as multiply by 1/2. So I'm going to pull out my 1/2. I get the integral of sine of I di left over. And so if I want to integrate sine, I'm going to guess cosine. But when I take the derivative of cosine, I get negative sine. So I needed a negative to begin with. So I get negative cosine of I is the antiderivative of sine. And then I just get a plus c. And so I'm left with negative 1/2 cosine of I, which remember I was 2x, plus c. And so that's how we're going to do that antiderivative. Again, we substituted in I. We made an easier problem. And then we continued on until we got out our final answer, which would be the negative 1/2 cosine 2x plus c. And again, it is a good idea to check your work here. Use a chain rule and take the derivative. Make sure you get out sine of 2x. If we do that, we'll get negative 1/2 times the derivative of cosine of 2x is negative sine of 2x times 2. The negative and the 2 cancels out with the negative 1/2. And so we're left with exactly what we wanted. And so that's our antiderivative. The next one on there is e to the negative x. And so if I want to finish this one, what I'm going to do is, well, the same thing is I can let I be negative x. Di is negative dx. So dx is negative di. And then when I substitute in, I get the integral of e to the I times negative di. And I'm going to pull my negative out. So I get the integral of e to the I di. And the integral of e to the I is just e to the I because the derivative of e to the I is e to the I. I need a plus c. And the last step is to plug in I. And so I get negative e to the negative x plus c is my general antiderivative for that one. I'm not sure what the next one is, so I'm looking it up real quick. Oh, the integral of 3x dx. Remember, we can pull the 3 out. And then we have a power rule. So this is x to the 1. So I get 3x squared over 2. Add 1 is 2. Divide by the new exponent is 2. The 3 stays. 3x squared over 2 plus c. And then the last one's just the integral of 12. Well, the integral of 12 dx is just, well, this is a constant, so I need a function whose derivative is a constant. So I would pick 12x here because the derivative of 12x is 12. And so I just get 12x plus c. And so if you're doing that as one big step, remember, you only need one c. You don't need multiple c's. All right. I'm just checking a couple of emails here and then try to go over some of the answers here. All right. So someone said question 5 from exam 3A. I got 2 of those. So I'm going to go back to exam 3. I just have to find it real quick. I think I know the one you're talking about, but I want to make sure before I ramble on about something that you don't care about. So, there we go. All right. So I believe that is, all right, the optimization one. So if we do the optimization one, what we had is I gave you a picture that looked like this. There was a triangle, there was a square, this was point A, this was point P, and this was point B. And what it said was, given that AB is equal to, I'm going to go with 6. I know one of the exams said 6, one said 9. I'm not sure which one was sent to me, but I'm just going to go with 6 because it's the same process. But assuming that AB is 6, find the place to put P that would minimize the total area of this object. All right. So now in order to do that, what we need to do is say, okay, well, this is a word problem. I need to read through, figure out what's given to me. And so we have that. Well, if we're reading through it, instead of writing it all down, I'll just kind of recap. It says that AP, this triangle formed here, is going to be an isosceles right triangle. I think the way I worded it on the exam was that each of the legs is the same length. So what that's really saying is that this length is equal to this length. Now, because I'm going to need to describe these things, I'm going to call this one X and this one X. So AP is equal to this length here. So I'm just going to call those both X to have something to refer them to. Now, on the other hand, it said that this was a square. So if I call this Y, this is also Y. Because that is a square, the side lengths are the same. So we end up with that picture there. Now what we wanted to do is we wanted to minimize the total area between the triangle and the square. So what we need to do is we need to find an area function. So I'm going to say that my area, I'm already using A here. So this is the point A. So I'm just going to call it area there. That'll distinguish. So the area is, well, you can find the area of the triangle is going to be 1/2 base times height. And so what we get here is that the base of the triangle is the X that I assigned. And the height of the triangle is also X because they're the same length. So we end up with 1/2 X squared. All right. What is the area of the square? Well, that's going to be just square is side length, so Y squared. And so the total area is going to be 1/2 X squared plus Y squared. And so our goal is to minimize this function on the given domain. Now, again, as happens for a lot of these optimization problems, we have two variables, right? So we don't know how to take the derivative of a two-variable function, just like we don't know how to take the integral of a two-variable function. So what we need to do is we need to get rid of one of these variables in terms of the other. So we need to find some way that they are related. Now, the way that they're related is, well, remember that this entire length is 6. So what we get is that if I take X plus Y has to be equal to 6. Now we can solve for either one of these. I think I'm going to solve for Y because I don't know, just because I chose it. If you want to solve for X, you can. It's just going to look a little bit different. But what I get here then is using this, I get Y is equal to 6 minus X. So what I can do is I can plug that in here for Y. And so I get that my area is 1/2 X squared plus, instead of Y, 6 minus X squared. And so that's my total area in terms of X. Now, in order to find the minimum point, remember that the minimum is going to occur at one of the local extremos and therefore at one of the critical points. So I have to find the critical points. In order to do that, I have to find the domain. So to start off with, notice that the smallest X can be is 0. It could be 0. That would mean that there's no triangle. There's just a square. It could also go all the way up to 6 because then you would have a triangle but no square. Now, if x was bigger than 6, that doesn't make sense because I need this y value to be positive, and that goes beyond how long those need to be. And if it was less than 0, that doesn't make sense either. So what we get is 0 is less than or equal to x is less than or equal to 6. And so we have our given domain. Notice that this is a closed bounded interval, and that is a continuous function. So if we have a continuous function on a closed bounded interval, what we end up with is we have to have a max and we have to have a min, and they have to occur at the critical points. So what we have to do is we have to find those, and the way we do that is we find the derivative. So the derivative, or the area prime, is just going to be, well, the derivative of 1/2 x squared is 2 times 1/2 is 1, so x. The derivative of this is a chain rule, so the derivative of the outside is 2 times the inside to the 1 times the derivative of the inside is -1. And now I'm going to just simplify that, so I get x plus 12 minus 2x times -1, and so I get x minus 12 plus 2x is 3x minus 12. And so I get that the derivative of area is 3x minus 12. Now, in order to find the critical points, remember, I have to find where this is 0 or undefined. And so the first thing I'm going to point out is that my derivative of area is undefined at the endpoints. So that's at x equals 0 and 6. So remember that at the endpoints, my function is not defined for x less than 0 or bigger than 6. So we don't have the secant from one of the sides, so the two-sided limit does not exist. So we don't have a tangent line, so there's no derivative at these 2 points. However, you want to remember that the point is you always need to keep the endpoints here if it's a closed interval. Now, where is the derivative of 0? So area prime is equal to 0 if 3x minus 12 is 0, or 3x is 12, and that is x is 4. I know I'm kind of running out of room here, but there's my point, is that, okay, I found my area in terms of x because I was able to get rid of the y in terms of x. I was then able to find my domain. I differentiated it, found the undefineds and the zeros to find the critical points. Now that I have the critical points, I know that because it's a closed bounded interval, my max and mins have to occur at one of the critical points. So all I'm going to do now is make a table. I'm going to say, here's my critical values. Here is my corresponding area. And so if I plug in 0, 4, and 6, I plug 0 into my area function over here. I get 1/2 times 0 is 0, plus 6 minus 0 is 6, squared is 36. And so that corresponds to having a square over the whole thing would give us a total area of 36. On the other hand, if we plug in 4, we get 4 squared is 16 times 1/2 is 8. 6 minus 4 is 2 squared is 4. So 8 plus 4 is 12. So if we place P 4 units away from A, then we'll end up with the total area of 12. Now, as the last one, we're going to plug in 6. If I plug in 6, I get 1/2 times 6 squared is 36 times 1/2 is 18, plus 6 minus 6 is 0. 0 squared is 0, so 18 plus 0 is 18. Now, if we remember, we were looking for the minimum area, so we're just going to find the smallest number. Here, 12 is the smallest number, so we would say that we have a minimum area of 12 when the distance from A to P, which I'm just going to write as AP, is equal to 4. And now I'm just writing it in context. The original one is how far from A should you place P? So the distance from A to P was X. X was 4. So I'm just writing down the answer as it was asked was find AP such that your area is minimized. And so that's what we're looking for. And so if we want to draw a picture, or if they wanted to know, this distance would be 4, this distance would be 2, this area would be 8, this area would be 4.
I don't understand.
So we end up with a total of 12. All right. My phone was talking to me. Does that one make sense for that problem? You guys have any more questions on the optimization one, or do you want to do another one like this? I'm trying to read chat and emails at the same time, and really not great at that, so let me know if you have any more questions. And I'm trying to look through the other problems here that we had posted. I'm seeing questions 12, 13, 16, 1, 10. All right, let me just write down all of my C's so that I remember. And then there we go. So then I'll start looking through those. If you guys want to look at different ones in particular, just kind of shout in the comments as we go, and I will do my best to keep all of that up. So there we go. Let's start with, I think I did one already. I might go back to that one in a little bit, but I'm going to start with 8 just to make sure I get through as many of these as I can. All right, so number 8 was find the derivative if you have a given function where you can't solve for y. I don't know why I erased that. I wanted that up there. All right, so what I have is a function where I can't actually solve for y. I have to just use what's given to me and implicitly differentiate. And so what I'm going to get there is, let's see, something like, I'm going to do a different one just to give you more examples, but let's say I had something like e to the x times y plus the square root of x plus y is equal to x cubed. Now, if I try to solve for y here, things just get really complicated, so it's really easier just to leave it as is and say, I want to find dy dx, so I'm going to implicitly differentiate, which means that I'm just going to take the derivative of both sides with respect to x. And then I'm going to see what I get out, and I'm going to hope that a dy dx pops out so that I can find what dy dx is going to be. And so that should happen as long as we have y's up here. And so I'm going to start off and just start taking my derivative. Remember, we can distribute across sums and differences. If I start with the easy one, because I like to just start with the easy one because it gives me confidence. The derivative of x cubed is 3x squared. Notice x is equal to x. It's just a normal derivative because it's the same letter. So I just get my 3x squared. Now here what I have is something a little bit more complicated. So I'm going to go off to the side and find the derivative of e to the x times y. Now there's two variables in here, so I can't just say normal derivative times or normal derivative. What I have to do is really go through this process and say, well, this is a chain rule. I have an outside and an inside function. My inside function is x times y. My outside function is e to the I. So now the derivative of the outside is e to the I. So outside prime times inside prime. And so what I end up with is, okay, e to the I there. And then when I take the derivative of the inside, I should actually do more work. So I'm going to find the derivative with respect to x of x times y. And now here we have a product rule. X times y is a product. So that's going to be second d first plus first d second. And so what I end up with is the second is y. The derivative of x, these are the same letters, so it's just the normal derivative is 1 plus the first is x. And now the derivative of y is, because these are different letters, I have to leave it as dy dx. So the derivative of the inside is going to be y plus x dy dx. So now I'm going to bring that back over here as the derivative of the inside. The derivative of the outside was e to the I times the derivative of the inside was y plus x dy dx. And the next step is I just plug in I was x times y So I get y plus x y dx. And so I'm just going to bring that up top and say, I'm going to not erase it quite yet, but I'm going to say this is e to the x times y plus x dy dx. Then I'm going to move on to the last part, and I'm going to say, what is the derivative of the square root of x plus y? So if I want to find the square root of x plus y's derivative, what I'm going to notice there is that, again, that is a chain rule where my inside function is x plus y, and my outside function is the square root of I. Now, the square root of I is I to the 1/2, so the derivative is 1/2 I to the negative 1/2, just using a power rule. And the derivative of the inside is, well, the derivative of x, because it's the same letter as 1, and the derivative of y, because it's not the same letter as dy dx. So the derivative inside is 1 plus dy dx. So if I plug that together, I get 1/2 times I, which was x plus y, to the negative 1/2, times the derivative of the inside is 1 plus dy dx, which is equal to 3x squared. And so what we've done is we've taken the derivative, we get an answer out, and so that's where we want to stop. Remember, I told you not to simplify this at all or solve for dy dx because it's just going to take too much time. So I would highly suggest leaving your answer like that. You differentiate it. Notice you have gotten out some dy dx's. We were careful along the way to use product rules or chain rules. And then we just remember that if y is not equal to x, we have to have this dy dx thing here. And so then that's what we're looking for out of that problem, is some type of implicit differentiation. All right. Does that make sense to everybody? You need another implicit differentiation one, or is that enough? I'll wait for some type of comment, or for a little bit anyway. The next one they had asked about was just the second part to that one, was something along the lines of, let's find the derivative of 2x plus 1 to the cosine of x. So if I want to find the derivative of that, how do I do that? All right, Jermaine, I will get to that one right after this one then. Let's see. Anyway, if I want to take the derivative of this is actually a complicated one, so I hope that you guys look at this one. So the idea is that I don't know how to take the derivative if I have a variable to a variable. So if I have an exponent, which is variable, and a base, which is variable, I don't have a rule for how to do that. So remember, what we wanted to do is turn it into a product. And the way we turn exponents into products is by taking the natural log. So what we're going to do is we're going to look at, well, instead of y is equal to 2x plus 1 cosine of x, we're going to say natural log of y is equal to natural log of 2x plus 1 to the cosine of x. And then what we get is natural log of y is equal to cosine of x times natural log of 2x plus 1. Now we're actually back in the last problem where we have an implicit differentiation problem. And so we're just going to take the derivative of both sides as is with respect to x. So I'm going to take the derivative with respect to x, the derivative with respect to x. On this side, the derivative of log of y is 1 over y times dy dx, because these are not the same letters. So we need normal derivative dy dx. And then on this side, we have a product rule. So it would be second times the derivative of the first is negative sine of x, plus the first is cosine of x, times the derivative of the second is a chain rule, is 1 over 2x plus 1 times 2. I know I went through the second part fairly quickly, but notice it's a product rule followed by a chain rule. We did similar examples to that in the last one. So we're going to go through, we're going to find an answer, and then we get something like this. Now notice again, you don't have to simplify, you can just leave it like that. That's what we're looking for. So the important part here is that if you have a variable to an exponent variable, you're going to end up having to take the natural log of both sides, differentiate, and you're going to get 1 over y dy dx is, and then you're going to have to use a quotient, or a product rule rather, along with probably a chain rule as well, in order to figure out what the derivative is going to be. All right, so practice exam 2, number 6. I just got to find that real quick. So there we have another implicit differentiation is y cubed plus x cubed is x e to the y. So if we have y cubed plus x cubed is x e to the y, and I want to find dy dx, again, we're not going to try to solve for y because that's not going to work out very well. So what we're going to do is just take the derivative as is on both sides. So I get the derivative with respect to x, and y cubed plus x cubed is d dx of x e to the y. And so what I get here is, well, I can distribute this, and so I need to take the derivative of y cubed and the derivative of x cubed. Now, if I take the derivative of y cubed, remember y is not equal to x, but there's only one variable there, it's just y. So I can take the normal derivative, is 3y squared, but then I have to remember to multiply by the derivative of y with respect to x because we have a chain rule there. So we get that the derivative of y cubed is 3y squared dy dx. Now for x cubed, well, x is equal to x, so now it's just a normal derivative. We don't have to worry about the extra thing on the outside. We just say, okay, well, the derivative of x cubed is 3x squared. Now, if we move on to this one, there's more than just one variable. There's an x and there's a y. So when we take the derivative here, we have to notice, okay, this is going to be a product rule because we're multiplying. So it's going to be second d first plus first d second. And so my second function is e to the y. My first is x. Or sorry, second d first. So the derivative of x is 1 plus my first is x. And now the derivative of e to the y is, well, the normal derivative is e to the y, but because y is not equal to x, we get times dy dx. So now if we plug that back in, we get, well, this derivative is e to the y plus x e to the y dy dx. So that's what we're looking for on that one. We take the derivative, notice the y cubed, we get 3y squared dy dx. These are the same letters, it's just the normal x squared. Here we have a product rule that we worry about first, but then when we're doing the derivative second, we notice that's y instead of x, so we need a normal derivative times dy dx for the derivative of the second. All right. Let's see. Well, I'm not sure what you mean by chain there, Gregory, so let me know on that one. In the meantime, I'm going to go back to these problems. So you're looking at the practice final. Number 10 would be the next one. All right, good. So we've got a related rates one here. So we have a 13-foot ladder. It's moving away at 5 feet per second, 12 feet high. So if I read through that one, remember for the related rates for any of the applications, we need to read through. We need to figure out what's going on, draw a picture, all of that put together. So if we look at this one, what we have some type of building, some type of ground, and then there's going to be a ladder here, and it says that this is a 13-foot ladder. Now, as we continue to read through, we're just going to write down what we see. Is we notice that they tell us right now this distance is 12 feet, and they tell us that the ladder is sliding away at 5 feet per second. So what we end up with is someone's on top of the ladder, the ladder's up here, it's falling some direction, or it's falling down towards the ground, and we want to know how fast is it falling, if this is moving at that speed. And so what we need to do is we need to figure out, okay, what's changing, what's variable. So if I look at this, I know the 12 is changing because the ladder is moving away. So I'm going to call this the base. So I'm going to call it B for base. So the base is 12 currently, but it is getting bigger because the 5 feet per second saying that the bottom's moving away from the building. On the other hand, the 13 is not changing because the ladder, it's staying as a 13-foot ladder. So we don't have to assign a variable there. But because the top's changing, that's going to be variable. So I'm going to call this the height. So the height is changing, so we give that a variable. Now, again, it's a related rate problem, so we're always going to have time changing as well. We don't need to explicitly write that down, but we do need to be aware of that. And so the next thing we have are the rates. So I have B, so I'm going to put dB dt. So the derivative of B with respect to, now in general, we're just going to take the derivative of any variable that shows up. But now we're doing it with respect to time because this is feet per second. So it's giving us the rate per time. So we're going to say dB dt. And now dB dt is the change in B with respect to time is going to be 5 because that's what's given to us. And now is it going to be a positive or a negative 5? Well, if we look at this, notice this is going away, so B is actually getting bigger. So I'm going to leave that as a positive 5 because B is increasing, which means a positive derivative. Now, we also need dH dt because we have an h here, so we need dHd, whatever we used up here was t, so we're going to use t again. So we get dH dt is, well, that's what we're looking for, so that's my question mark. Now, the hard part is to figure out how these things are related. How is B related to H? And how is that related to 13? And so we look at this and we notice that, yes, it is a triangle. And so we could talk about different things. And so really I'm looking for keywords here is they're telling me about this side and this side. They don't really ask about the total perimeter at all. If they said perimeter in the problem, I would use a perimeter equation. They don't really talk about area at all in the problem. If they had, I'd use an area equation. So they just leave it as the sides. So what we need is an equation that just relates to the sides and ignores the other stuff. And so that's going to be, well, this is a right triangle, so we can use the Pythagorean theorem. And what we get is b squared plus h squared is 13 squared. Notice that the 13 is constant, so I don't need to plug a variable in over there. I can't put 12 in for b because it's not going to be staying 12. It'll be 12 at this moment, but it won't be there forever. So I have to leave b in here instead of 12. And so what I get now is, okay, I have an equation relating b and h. So there's b, there's h. And so from that, I should be able to find dH dt if I know dV dt. So now once I get my equation, the next step is to differentiate. So I'm going to implicitly differentiate again. So this is the application of the things we've just been working on. And so I take the derivative of both sides with respect to time. And so if I go back, remember b is not equal to t. So it's going to be a normal derivative times dB dt. So the derivative of b squared is 2b times dB dt. So I get 2b dB dt. Derivative of h is h squared is dh dt because h is not equal to t. And the derivative of 13 squared, well, 13 squared is a constant, so the derivative is just 0. All right, so now if we continue on, what we need to do now is just find dH dt right now. And so right now we know that what b is, we know what dB dt is, so we can start plugging things in. So we can say, okay, right now, 2 times b is 12. dB dt is 5 plus 2 times, well, I don't know h, but it's not what I'm looking for, so I need to find h. So when I get into this situation, I need to look back over my equations and say, can any of these help me find h? And well, if we use the original equation, the b squared plus h squared is 13. Right now we know b is 12, so now we can plug in 12. So we get 12 squared plus h squared is 13 squared. So we get h squared is 13 squared minus 12 squared, which is 169 minus 144. 169 minus 144 is 25. So the square root of 25 is 5. Because it's a distance, it's going to be positive. So we get a 5 there. And then we get dh dt. And we leave the dh dt because it's what we're looking for. And then we just solve. So we subtract this portion, divide by this portion, and we're going to end up with dh dt is negative 12. So now we found the solution to our model. What we need to do is we need to find the solution to the original problem, which asked how fast is the top of the ladder falling. So how fast is the top of the ladder falling? Well, the top of the ladder is falling at and then, so we have 12 here. Notice the negative means it's getting smaller. We imply that by saying falling. So it's falling at 12. And then the units are going to be whatever the units were here. So length is in feet. So h is feet. Per time is seconds. So the top of the ladder is falling at 12 feet per second. And so we have finally finished that one. I know that the related rates are everybody's favorite. So I hope that you enjoyed that thoroughly. All right. Everybody okay? We're still moving on. Do you have new questions? Anything like that popping up before I just go on to the next one? All right. Well, I'll just assume everything's okay. That was number 10, so I think number 11 would be up next. Like I said, if you want something else in particular, just speak up and we'll try to get to it. Number 11 is find the equation of the tangent line, and number 12 is find the equation of the tangent line. And so we looked at number 12 a little earlier, so if you're here then, that's okay. We'll go through and do a different one this time around. But I'm just going to do one problem for both of these. And so let's suppose I pick a function, let's say f of x is e to the x, and I want to find the linear approximation at x equals 0. So now actually number 11 and number 12 are really saying the same thing. And number 11, it says find the equation of the tangent line. And number 12, it says find the linear approximation. But what I told you is that the linear approximation is just the tangent line. So in both cases, we find the equation of the tangent line to the function at the given point. So let's go through that. The equation of a tangent line is y equals m times x minus x naught plus y naught. So in this case, they give us the x naught, or the initial x is the 0. And then the y naught is the function value at the point they give us. So they want us to find f of 0. So what is f of 0 is e to the 0 is 1. All right. Now, the slope is, or the slope of the tangent line is the derivative at the point. So that's going to be f prime of 0. So we need to find f prime of x first. Well, the derivative of e to the x is e to the x. So f prime of 0 is, again, e to the 0 is 1. So now if we plug that all in, we get y is equal to 1 times x minus 0 plus 1. And so y is equal to, and this one I'm going to simplify because I'm going to use it in the next step, but it's okay to leave it like that. So my linear approximation, or the equation of my tangent line, is y equals x plus 1. Now, the second part says, what is, or find e to the 0.1. I know is a different problem on the actual part of the exam. But if I went to approximate, rather, not find, but approximate e to the 0.1, how would I do that is, well, what I notice is that really f of x is e to the x here. And so here all I'm doing is plugging in 0.1 for x. What we just got done saying was that this function is approximately x plus 1 as long as x is close to 0. Now, is 0.1 close to 0? Well, I guess that's up to you, but I think it's close enough that we can at least get a decent approximation. So what we're going to say here is that e to the 0.1 is equal to my function value at 0.1 is approximately equal to my linear function that I just came up with, or my tangent line at 0.1. So what that means is I'm going to plug 0.1 in for x. So I'm going to get 0.1 plus 1 is 1.1. What does that mean is that e to the 0.1 is approximately 1.1 using my tangent line, or using my linear approximation. And so when that one shows up on the test, remember, linear approximation means tangent line. Then if they ask you to approximate a value, all they're asking you to do is find the x value and plug it into the approximation you just found. So if it was e to the 0.2, you plug 0.2 in for x, or e to the 1 even, you could say plug 1 in for x. And you'll get an approximation for what that value is going to be. All right. Let's make sure no more questions are coming up. You guys are getting quiet. You guys are still there, right? I see 8 of you there. Hopefully you just haven't fallen asleep. Anyway, the next one up here was 13. So if I look at that, I have a related rates problem again. And so what I have, I'm sorry, I have a linear approximation problem again. And so this one, it just says approximate the change in volume of the sphere when its radius changes from r equals 5 to r equals 5.1. What I told you guys during class was that for that one, it's going to be worded a little bit differently, and they're just going to say approximate or find the change in volume when r is equal to 5. So the important part here is really beyond anything else, just it's a reminder that the change in volume is just going to be, well, the change in volume with respect to the radius is just going to be the change in volume with respect to the radius is dv dr. The change in volume with respect to radius. And so what they're asking is just find dv dr when r is 5. So now, if I pull this together, what I get is, well, remember that the volume was 4/3 pi r cubed. So I need to take the derivative of both sides. And so I get dv dr is the derivative, rv prime. And now I can factor out the constants. So the 4/3 pi, I'm left with r cubed. So I get 4/3 pi times 3r squared. And so the derivative of volume with respect to radius is 4/3 pi 3r squared. Now the last thing they want us to do is realize that we're trying to find it when r is 5. So we would plug in r equals 5, and we get 4/3 pi times 3 times 5 squared. And if I do this correctly, the 3's cancel. 4 times 25 is 100 pi. So dv dr is 100 pi. And that's what I want you guys to get from that problem. Is just realize that when they're asking for the change in volume with respect to r, it is the dv dr. So find dv dr when r is 5. All right. Number 16. All right. Let's look at that one real quick. So what we have for number 16 is we have a function given to us that looks like this. So 1, 2, 3. All right, so we have something that looks like this. And now if we read the problem carefully, they tell us that this is f prime. That's actually the hardest part of the whole problem, is to realize that this is the derivative, not the original function. So if we realize that's the derivative, then we can answer the rest of the questions. And the next one is, find when is f of x increasing? Well, f of x is increasing if, remember that happens if and only if the derivative is greater than 0. But now remember, this is the derivative function. So when is a function greater than 0 is that if it's above the x-axis. So where is this above the x-axis? Is, well, it crosses at 3 and it's above everything over here. So I would get that it's increasing when x is greater than 3. So that's from 3 to infinity. When is it decreasing? Well, the original function is decreasing if the derivative is negative. Therefore, this function is decreasing. Well, it's below the x-axis all the way up to 3. So from negative infinity to 3. So this function is decreasing from negative infinity to 3. Where are the critical points? Well, the critical values, rather, are where the derivative is 0 or undefined. So notice that the derivative, this function, is 0 when it crosses the x-axis. So it crosses the x-axis at x equals 0, and it crosses at x equals 3. So my critical values are x equals 0 and 3. I am decreasing from negative infinity to 3, increasing from 3 to infinity. And so if we notice, that means my actual function is going to look like this. Roughly, just increasing and decreasing. And so what we're going to have is, we will not have an extrema at 0 because we're going to decrease, then decrease. We will have a local minimum at 3. Actually, we'll have a local minimum at 3, so we would say also local minimum at x equals 3. And so for this problem 16, those are the questions they ask you. Where is it increasing? Where is it decreasing? What are the critical values? And what for the critical values are the minima or maxima or neither? And so what we would say here is that at 3 we have a local min, at 0 we have neither, but those are both critical values, and I'm increasing from 3 to infinity and decreasing negative infinity to 3. The next part's going to be, where is this function concave up and concave down? So now I'm going to go back and do this all over again, and I'm going to say that f is, and I'm going to write this down just to keep everything straight, f is concave up if and only if the second derivative is positive, and it's concave down if and only if the second derivative is negative. But now, because we have the derivative function up here, I'm going to say that the second derivative is positive if the derivative of the first derivative is positive. So now if the derivative of a function is positive, that means that the original function is increasing. So I know that's hard to keep track of, but if we go through, second derivative means the first derivative is increasing. So if I'm looking for where the second derivative is positive or where this function is concave up, I'm actually looking for where f prime is increasing. So if I'm going to find where it's increasing, notice I'm going up here, up to here, and then I start increasing here to here. So what I would say is that f prime is increasing on negative infinity to 0, union 2 to infinity. Because we'll notice here that the derivative of the derivative is 0 here. It's positive on this side. The second derivative is positive over here because it gets to be 0 here. And then next we're going to be concave down if and only if the second derivative is negative. That means that my first derivative is decreasing. And while this function is decreasing from 0 to 2. So my original function is concave down if this function is decreasing. So that's the interval 0 to 2. What then are the inflection points? Well, I have inflection points when I change concavity. So I'm going to have inflection points at x equals 0 and x equals 2. And so that would be the rest of that question was It's concave up if the second derivative is positive, which means the derivative is increasing. So I look at the function, determine where it's increasing, and I write those intervals down. It is concave down. The second derivative is negative, so that means my derivative is decreasing, and so I found it was decreasing 0 to 2. And then at the change points here at 0 and at 2, those are my inflection points, and so those are the ones I'm going to write down for that problem. All right. All right. Now we're at, sorry, I'm just trying to read this. The practice exam 3, number 5, last two parts of 5. Okay. I'm going to pull up practice exam 3, number 5. I appreciate all the questions, guys, because otherwise I had no idea what to talk about. So. All right. Now, just to make sure, Jermaine, that was the limit ones, right? I think I renumbered them because I had to rewrite a practice exam for someone else. So I think you mean the limit ones. I just want to make sure before I start doing something, so tell me if I'm wrong. So that is, what was the limit as x goes to 1 of natural log of x over x minus 1? All right, good. So now if we look at this one, we're going back to limits again. So anytime we're doing limits, we should plug in the number and see what happens. So I'm going to plug in 1. I get natural log of 1 over 1 minus 1. And now natural log of 1 is, well, e to the 0 is 1, so natural log of 1 is 0. 1 minus 1 is 0. So we end up with the 0 over 0. All right. If we had gotten a number out, we'd write that, we'd be done. But we didn't, so we move on. And so what we get here is, well, 0 over 0 means that we have an indeterminate form, so we do more work. And here we're going to use L'Hopital's rule. And that's what we're going to use for pretty much all the limits, except for the definition of derivative. And so I'm going to have the limit as x goes to 1. Well, the L'Hopital's rule says derivative of the top over derivative of the bottom. So the derivative of natural log of x is 1 over x. And the derivative of x minus 1 is 1. And so now I have a new limit. I calculate again by plugging in. If I plug 1 in, I get 1 over 1 over 1. 1 divided by 1 divided by 1 is 1, which is a number. So therefore, I am done. So we can move on from this one. And so in general, that's how we would work with L'Hopital's rule is we start off with a complicated one. We take the top derivative of the bottom, and it leads to a problem that we can then actually calculate. Now, the next one was the limit as x goes to 0 of cosine of x minus 1 over x. Just making sure I'm reading that correctly. So I have cosine of x minus 1 over x. Now, if I plug 0 into here, what I get is cosine of 0 is 1 minus 1 all over 0 is again 0 over 0. So again, I end up with my indeterminate form. So I have to do more work. How do I do more work? Is I take the derivative of the top over the derivative of the bottom and use L'Hopital's rule. So what I get is the limit as x goes to 0 of, well, the derivative of cosine is negative sine. The derivative of negative 1 is 0. And the derivative of x is 1. Now at that point, we have a new limit. So we plug in again. And I get negative sine of 0. Well, sine of 0 is 0. So negative 0 over 1. Notice now that 0 over 1 You don't want to use L'Hopital's rule again because we don't have 0 over 0. We have an actual number. I know 0 is a weird number, but it's still a number. So that is our answer. We are done. My limit is 0. All right. Now for the next one, we're going to end up with something that looks similar, but not quite the same. So what we're going to have is the limit as x goes towards infinity of x times natural log of 1 plus 2 over x. And so what we get is, well, same way we did before, is we're going to plug in. So we get infinity times natural log of 1 plus 2 over infinity. So this looks like 0. So this looks like natural log of 1. And so we had just talked about natural log of 1 looks like 0. So we get infinity times 0. So what we're going to get here is infinity times 0 is an indeterminate form, but we can't use L'Hopital's rule because it's not a quotient. So what do we need to do instead is we need to convert the product into a quotient by dividing by the reciprocal of one of these instead of multiplying. All right. Now, I'm just going to help you guys out here. There's a couple different cases. If you get x, natural log of x, which one should you put on the bottom? Well, for this one, what we're going to put on bottom is x. We're going to get natural log of 1 plus 2 over x to the negative 1. So instead of multiplying by x, we divide by x to the negative 1. That's the same thing. And so we've now got, in this case, 0 over 0, so we can use L'Hopital's rule. What I was going to point out, though, is that it's not always going to be x log of x. What if I had x times e to the negative x? Limit as x goes towards infinity. I get infinity times 0 again here. So now which one do I want to put on bottom? Here is, in this case, I actually want to move the e to the x to the bottom. Here I'm moving the x to the bottom, but here I'm going to move the e to the x to the bottom. And I'm going to rewrite this as x over e to the negative x is e to the x. So x over e to the x, and then it makes my life easier. If I had something like the limit as x goes to 0 of x times cosine of x, well, I would get, sorry, that's not the one I wanted. I wanted cosecant of x. What I get here is 0 times infinity. In this case, when you have a trig function, you should move the trig function to the bottom. So you get the limit as x goes towards infinity, I'm sorry, 0, limit as x goes towards 0 of x, divided by cosecant to the negative 1. Well, cosecant of x is already equal to sine of x, 1 over sine of x. So 1 over sine of x is just sine of x. So now that's worth rewriting, and it's just x over sine of x. So now if you run into these product ones, we dealt a lot with the natural log ones. With the natural log ones, we leave the natural log up top, and we pull the x to the bottom. If you have an e to the x, or you have a trig function, or in most other cases, you're actually going to leave the x up top and pull the other function to the bottom. Now, if you do it the wrong way, you can still use L'Hopital's rule. What you're going to end up with, though, is that you're going to end up with a more complicated answer when you're done than when you started. So if I try to do e to the negative x over x, I'm going to end up with negative e to the negative x over negative x to the negative 2. You notice that I'm adding to the exponent instead of subtracting, so I'm making the problem more complicated instead of less. If that happens to you, switch which one's on top, try L'Hopital's rule again, and that should allow you to get to the correct answer without making things more and more complicated on yourself. So just a hint there on kind of things that might come up besides just the x log of x. Now, going back to the original problem, though, we now have, again, a 0 over 0, so we use L'Hopital's rule. So now we need to take derivatives. So I'm going to go off to the side and do these because these are complicated enough that it's worth it. So I get the derivative of natural log of 1 plus 2 over x is a chain rule. My outside function is natural log of I. My inside function is 1 plus 2 over x. So the derivative of the outside is 1 over I. And the derivative of the inside is, well, the derivative of 2 over x, which is the derivative of 2x to the negative 1, which is negative 2x to the negative 2. So now if I bring that together, I get that the derivative of the top is natural log of I. I'm sorry, derivative of the top is derivative of the outside is 1 over I times the derivative inside is negative 2x and then negative 2. And then plugging I back in, I get 1 over 1 plus 2 over x times negative 2x and then negative 2. So notice now that wasn't a trivial derivative. We can't just write the answer down. It's worth going off to the side, doing the work, pulling that back together so that we make sure we do it correctly. But we get the derivative there is in fact 1 over 1 plus 2 over x times negative 2 to the negative 2x to negative 2. And then the last thing is we have to take the derivative of the bottom. So that's a power rule of negative x to the negative 2. Now, again, it looks like we actually made it more complicated. And so sometimes that's okay. We want to say, can we simplify? Now, if we made it more complicated and we couldn't simplify, that's what I was talking about earlier. But here, it looks more complicated, but we can simplify because these x to the negative 2's cancel, the negatives cancel. And what I'm left with is 2 times 1 plus 2 over x. And now that looks a lot easier than the previous problem. So to calculate that, again, we see what happens as x goes towards infinity. So we get 2 over 1 plus 2 over infinity. Well, 2 over a huge number is a really small number, so that's 0. So 2 over 1 plus 0 is 2 over 1 is 2. 2 is a number, so that's the answer we're looking for. All right. Does that one make sense at all? Yep, I will go over number 22. As soon as I'm done with this one, go ahead. Did you guys follow this one at all? You're not saying anything, so I'm just going to go with yes. And I'm going to move on to the next one because the next one is complicated as well. And so let's suppose I end up with something that looks like x to the x. So what is the limit as x goes to 0 of x to the x? I want to point out that earlier we did a derivative function where we had a variable base and a variable exponent, and we said that those things are awful. We don't have any nice rules for them. Well, we don't have any nice rules for this one either. But if we plug in 0, we get is 0 to the 0. And what is 0 to the 0 is, well, we don't know. If you want to think about it one way, 0 to anything should be 0, but anything to the 0 should be 1. So I'm getting out 2 different answers, so really I can get out anything I want. So instead what I have to do here is more work, and so I want to use L'Hopital's rule, but I can't because it's not a quotient. If it was a product, we could convert it into a quotient, but it's not even a product, it's an exponent. So I have to turn an exponent into a product by using a natural log. Okay. So what I'm going to do is I'm going to rewrite this one, and I'm going to say the natural log of the limit as x goes towards 0 of x to the x. But now I can't just take the natural log, so that changes the problem. So I'm going to have to say e to the natural log because those cancel out. I'm left with the original problem. But now I can use my natural log rules. And one of the rules in particular is that I can pull the natural log to the inside of the limit. So I get e to the limit as x goes to 0 of natural log of x to the x. Now, generally, I go off to the side and say the limit as x goes to 0 of that top portion, and when I'm done, I'll plug my answer back in because it's just a little less to write each time. So now the whole point of taking the natural log is that I can pull the exponent out front. So I'm going to rewrite this as the limit as x goes to 0 of x times natural log of x. Now, if we plug 0 in, we get 0 times natural log of 0 is, well, as x approaches 0, we're actually going to get out negative infinity here. So what we end up with is, well, okay, that's indeterminate. 0 times infinity is indeterminate. So what do we need to do? Is we need to rewrite this as a quotient instead of a product now. So I'm going to pull the thing to the bottom. Remember, there's a natural log here. So what we're going to do is pull the x to the bottom. So I get x to the negative 1. So what I end up with is the limit as x goes to 0 of 1 over x divided by, and the derivative of this is negative x to the negative 2. Now again, I'm going to simplify, and so if I divide by x to the negative 2, that's the same as multiplying by x squared. So I get the limit as x goes to 0 of 1 over x times negative x squared, which is the limit as x goes to 0 of negative x, which is 0. So therefore, the limit as x goes to 0 of x log of x is in fact 0. But remember, that was just the top over here, so we're going to bring this answer back. So we get e to the, that limit was 0, and e to the 0 is 1. So the limit as x goes to 0 of x to the x is in fact 1. And so again, if we have a variable base to a variable exponent, we use a log to turn that into a product instead of an exponent. All right. I hope that helps. Hope that one goes well for you. All right, number 22 on the example exam. So we'll go to that one. All right, so what I want to do is, if the population of bacteria is growing at an instantaneous rate of change of 2 to the t million bacteria per hour, what does the definite integral from 0 to 1 of 2 to the t dt represent? All right. So all I'm going to do here is actually just look at what's going on. If I integrate, now this is the rate of change of bacteria. So the instantaneous rate of change of bacteria is the change in population of bacteria with respect to time. So that's the first thing we need to see, is that the rate of change is the derivative. So the rate of change of the population of bacteria with respect to time is the rate of change of population with respect to time is dp dt. So now what they ask us to do is take dp dt, which is equal to 2 to the t, and integrate from 0 to 1 dp dt with respect to time. Now, really, the whole purpose of this problem is just to see if you knew the fundamental theorem of calculus, which says that if we want to find a definite integral, we have to find an antiderivative. Well, since we're giving a derivative, to find the antiderivative of the derivative is just the original function. So the antiderivative of the derivative is the original. So really, this is just p of t. So the population as a function of time. And now they're saying evaluate that from 0 to 1. So that means evaluate from 0 to 1. So the antiderivative is the original. I evaluate, plug in 1, plug minus 0. And so I get p of 1 minus p of 0. So it is a really long-worded question saying, use the fundamental theorem to say that the antiderivative of a derivative is the original. Plug in 1, subtract off 0, and what we get is the change in population if I move from time equals 0 to time equals 1. That is, this is y2 minus y1, or p of 1 minus p of 0. And so that's what they're looking for here, is you find the original, you plug in 1, you subtract off, plugging in 0. Now, the next part is they want you to find what? Something. What does p of 0, they use f here instead of p, but I'm going to stick with p for population. What is p of 0 plus the integral from 0 to 1 of dp dt? What does that represent? Well, if we just follow along the same argument, we just said this was p of 1 minus p of 0. So what we get is, just plug that in, p of 0 plus p of 1 minus p of 0. The population at time 0 cancels. And so what we get is that the population at time 0 plus the integral from 0 to 1 of dp dt is just the population at time 1. So what they're giving us is well, okay, if I combine these together with this, I get just the population at time 1. And so they don't even ask us to calculate that, which is fine. All they want us to do is recognize that by the fundamental theorem of calculus, if we integrate a derivative, we get the original problem. Then we just plug in one value and subtract off, plug in the other. And so that's what they're looking for out of that problem. Does that help you out there? Does that make sense? Let me know if it doesn't, if you need more help with that one. If not, did you guys have any other questions you wanted to go over? I'm going to check my email, see if there's anything waiting for me. No, I'm not seeing anything. You are welcome, Griffin. All right. If you guys don't have any other questions, I'm going to sit here quietly, or I'm going to end up logging off a little bit early. So I think we've gone over most everything that's going to be on there. If you guys can think of something, I'll give you a couple minutes. And after that, I might end the broadcast early if there are no more questions. So let me know. Number 25 of the sample final. Is there a 25 on the sample final? Or do you mean the final review? I think here it's for 25 of the, not the sample final, but rather the final review was something like find y equals y of x if the second derivative with respect to x, there should be a square there, is equal to 8x, and dy dx is equal to, at 0 is equal to 2, and y of 0 is equal to 0. All right, good. Just making sure I have the right one here. So if I try to track this all down, I'm going to rewrite it in notation that we've been using. And so really what they're telling me here is that the second derivative, or f double prime of x, is equal to 8x. The first derivative at time 0 is 2, and the original function at time 0 is 0, and they want us to find f of x. So now, we haven't really dealt with anything quite like this, mainly because of the time crunch in the end. We didn't spend a lot of time trying to integrate second derivatives and working with, basically if we work with acceleration, we get questions like this, and then we want to find position. And I have some that are normally worked into the schedule, but those are one of the things that got weeded out. And I really don't, just to be honest, I don't think anything like this is actually going to be on the test, but in case it is, what they're saying here is the second derivative is 8x. So if I want to find the first derivative, remember the second derivative is the derivative of the first derivative. Therefore, the first derivative is the integral of the second derivative. So again, this is a fundamental theorem one. If I want to find the first derivative, I have to integrate the second derivative. And then they also want the derivative at 0 to be equal to 2. So now there's a couple ways we can do this. I'm going to use the, let's find all general antiderivatives and then solve for c when we're done. So what we get here is, we're going to integrate 8x. And if we integrate 8x, what we get is I'm just going to take 8x to the second, divide by the new exponent. We add 1 to 1 is 2, divide by the new exponent is 2. So we get 8x squared over 2, or 4x squared. But now remember, because we're finding the general antiderivative, we need a c there. So what happens is I can use this to find c. The way I do that is 2 is equal to f prime of 0 But f prime we just decided is this. So if I plug 0 into here, I get 4 times 0 squared plus c. So the 0 cancels, and I just get c is equal to 2. So then what I get is f prime of x has to look like this with some c. And we just said c has to be 2. So I know that my derivative has to be 4x squared plus 2. Now we start the problem all over again. We know that the derivative is 4x squared plus 2. Therefore, the original function is the antiderivative of the derivative. So if I now want to find f of x, I'm going to say that f of x is the antiderivative of f prime, which is 4x squared plus 2 with respect to x. Again, I'm going to get a c out, and I'm going to have to solve for c using my f of 0 is 0. So I'm just going to integrate. The antiderivative of this is 4 stays, so x cubed over 3 plus 2x plus c for my constant of integration. And then I'm going to follow the same process. 0 is f of 0, but f of 0 looks like this. So that's 0 plus c is c. So therefore, 0 is c. So f of x has to look like this. 4/3 x cubed plus 2x plus 0, because 0 has to be c. And we're left with the original function. So we've done this one step at a time in class as far as we have a derivative, find the original, we integrate. We have a c here, we find c, we did do that. We didn't do it twice like it has here, but really this is just doing the same thing twice in a row. And then, as I said, that would be something like if you have the acceleration and you want to find distance, you'd have to integrate twice, because the integral of acceleration would be velocity, and the integral of that would be position. And we mentioned the velocity, the position when we did the lab, but we didn't talk much about acceleration, which is why this didn't really come up. All right. Any other questions on there? You are welcome. All right, well, thank you guys for stopping by. There's only a couple of you left, so I'm going to actually just go ahead and call it there. I know I said I'd be here till 1, but I think I've answered most of the questions. If you do have more, feel free to email me, and I'll try to get back to you so that I'll give you the answers the best I can. And other than that, though, good luck, guys. I really hope you do well. I hope this helped. Let me know if it did or not. Leave a comment or something. But otherwise, good luck on your exams. I'll see you guys tomorrow or Wednesday or Thursday, depending on when your final is.